How's it going, everyone? Mr. Geyser here with lesson 8b on the tangent function. For the tangent function, we don't have a concept of amplitude since the range of the tangent function is really all real numbers. The role of a will provide the magnitude of that vertical stretch in the graph of the tangent function. Think of this as the stretching factor for the a value. Next, let's take a look at some vertical and horizontal transformations. In example 5, we want to try and state these transformations, graph each of the functions, state the period, and show all of these asymptotes when we introduce this c, the phase shift, and d, that vertical shift. For part A and B, we're going to find the a, b, and period for both of these equations, and then we'll graph them one at a time. For part A and B, that amplitude is just going to be that leading number of 2 for A and 3 for B. Once we find our amplitudes, our next step is to find that b value. In the case for A, there's no b value, there's no coefficient in front of x. But for B, we do have a coefficient in front of x as 1/2. As that reminder, tangent of x uses that new period equation of pi over b. For part A, our period is going to be 1 pi. And for part B, our period is going to be 2 pi. Now we want to try and identify if this has a phase shift or a vertical dilation. For part A, we do have a vertical translation, not a vertical dilation. We do have a vertical translation of -1. For part B, we do not have a vertical translation. Now let's put this together and graph part A. That first step is to always grab that origin point there, but this time we're going to bring it down towards that midline. Now once we have these 3 points, or as many points as we're able to graph, making sure to keep them exactly a period length away, we split them right in half to find where those vertical asymptotes occur. Once we find these vertical asymptotes, we find the in-between sections between the vertical asymptotes and those intercepts of the midline to find where these positive and negative amplitudes go. Keep in mind, this positive and negative amplitude is based off the midline. So we're going a full 2 units above the midline and 2 units below the midline. Now wherever these occur here, we know that since we have a positive tangent, we're going to approach from that negative direction. So we go into that halfway point, down to that negative amplitude. Then we go to that halfway point, and then up to that positive amplitude. Once we have each of those 5 key points for each of the periods of our tangent functions, we're able to graph them all together. Now, what I'd like you guys to see for part B. For part B, this is how I'm expecting individuals to graph tangent functions. We're not going to have any scaffolding, any like b or p divided by 2 or period length. This is how I'm expecting you guys to graph these functions. First, plot as many of those points as you can. We're able to plot these 3 these 3 intersection points on our x-axis since we don't have a vertical translation. Then split them in half and just make those vertical asymptotes. Once you split these in half, keep in mind what your negative and positive amplitude are and where that in-between section of your intercept and that vertical asymptote is. Once you graph these amplitude points here, you're able to connect all of them together to graph your tangent function. Now, the final step for both part A and part B is to state where all the asymptotes occur for each of these graphs. Notice that for part A, we can use this equation here, the argument of b times x plus c, where this argument is just what's inside of that tan, is equal to the equation from our tangent of x functions asymptotes. This here is the parent function's asymptote equation. So we set that equal to the child's function's argument. Once we set that equal to each other, we simply fill in our values for b and c. In this case, b is just equal to 1, and we don't have a c value, so it's just a 0. So our asymptote equation for part A is just going to be x is equal to that pi over 2 plus or minus pi times k, where k is equivalent to any integer. We write that compactly by saying k epsilon zeta. Now we want to try and describe the asymptote equation for part B. Same steps. We take that argument there of 1/2 x, the argument from our tangent, and set it equal to the asymptote equation of our parent function. We now have 1/2 x plus 0, because there's no phase shift, and then we simply solve for x. To do that, we're really just multiplying both sides by 2. And for part B's case, we get that x is going to be equal to pi plus or minus 2 pi times k, where k is equivalent to any integer. In example 6, we're going to do the same thing as example 5. We're going to use that transformation to graph these functions. However, what I'd like you guys to see is how we're going from these tangent lines to our child functions. We're really starting with this tangent graph, and if we were to add an amplitude of 2, we're really just stretching that graph up about twice as much. However, if we make it negative 2, notice how we're going to flip it across the y-axis. It flips across the y-axis if we have a negative amplitude. Now we want to try and introduce that c value here of that phase shift. We're just pushing that graph over to the left pi over 2. Now that we have that graph fully plotted, we're able to grab that a, b, and c value, and since b is equal to 1, our period is just equal to pi. The main thing I want to focus on with these problems here are going to be these asymptote equations. For these asymptote equations, we want to take the argument of our tangent and set it equal to the equation for the asymptotes of our parent function. This argument here would be verbatim whatever inside of that tangent function. So we bring down that 1 for b and that plus pi over 2. Since 1 is in front of our x there, there's no need to bring it in. So we're just going to subtract that pi over 2 from both sides here to get x is equal to pi times k. One important thing to notice is that we originally had this plus or minus in front of that pi over k. You can keep plus or minus all the way down. Luckily for us, we will never have a like term like this, meaning we'll never have some k value on the other side of the equation, so the operation of this term will never change. We might divide it, we might multiply that term, but the actual operation of plus or minus won't change for this term here. Once we have that x equals equation, we can say that the asymptote equation is plus or minus that pi times k, where k is equivalent to any integer. Let's do the same process now for part b. For part b, here is our parent function of tangent of x. If we were to add that vertical stretch, that amplitude of 3, we're really just taking these points and stretching them 3 units higher. Now we want to try and introduce that 2x, where we're just changing the period and we're doubling the amount of tangent lines inside this graph. Once we're doubling that here, notice this phase shift. I'm going to push all of these graphs to the right, a full unit of pi. Ready? We're going to go from this graph here to this graph here. It's the same. Basically, the only thing difference is that technically speaking, all of these points shifted a full pi over, but since there's already a tangent at pi from 0, it doesn't really look like we shifted. That last and final step here is to actually have a vertical shift of 2 units up. Our new midline is way up here at plus 2. Now this looks a little bit messy, so let me just try and recreate it here while we're stating all of those a, b, c values. We're able to identify all of these intercepts here right in between them, all of this midline here. But to clean it up a little bit, the equations a, b, and c are just 3, 2, and pi. The period now is pi over 2. We're doubling the amount of graphs inside of this plotted area. That c value does have that phase shift to the right-hand side because inside the argument, it has a negative operation. That next step here is to simply solve out for the asymptote equation. For that asymptote equation itself, I want to try and just bring it over on this side here, just so I have some room. And again, we're just taking the actual argument inside of that tangent equation and then just plugging it in to the other side. We set that argument to the equation for our asymptotes of that parent function and then solve for x. That first step here is just to add pi to both sides, and then we get 2x is equal to 3 pi over 2 plus or minus that pi times k. And again, that operations here aren't going to change. Even if we divide both sides by 2, we just simply get pi is equal to 3 pi over 4 plus or minus pi over 2 times k. Now that we have that asymptote equation, we just need to specify that these k values are equivalent to any integers. For both of these problems here, the main focus I wanted you to see is how we're going from tangent of x in each of these steps here to transform these child functions today. Now for example 7. For y equals 3 times tangent of x over 4 minus 2, we want to find these following 5 key characteristics. The first step for this problem, at least for me, is I do want to try and use some type of calculator to graph this function. For graphing this function, our TI-84 calculators aren't going to give us these vertical asymptotes here, those midline, or those intercepts here, but we can solve them using arithmetic. The first step is to identify what this left vertical asymptote and this right vertical asymptote is for our equation. All we do is we take this argument of x divided by 4 and make it equal the asymptote equation for our parent function of tangent of x. For the left-hand side of this asymptote, we just want to set k to be equal to 1, or we're going to set the right-hand side of our asymptote to 0. What this achieves is we have these two equations where we have negative pi over 2 on this left-hand side and positive pi over 2 on that right-hand side. Once we have the right and left asymptote equations created, we simply solve for x for both. That first equation for our first vertical asymptote occurs at negative 2 pi, and that second vertical asymptote occurs at 2 pi. We now want to try and find the period based on our b value. We can see that our b value here is going to be equivalent to 1/4, and as that reminder, that p equation for tangent is still going to be pi divided by b. So we simply do pi divided by 1/4, or 1/4, which is really just multiplying by 4. So our period length is equal to 4 pi. We now want to describe the 3 transformations of our child function. The first transformation that occurs is going to be this vertical dilation of a factor of 3. Second, we're going to have a horizontal dilation of a factor of 4. And then third, we're going to have a vertical shift down 2 units. If we take a look just at this graph though, we want to try and state in part D, what's the intervals where the function is concave down. If we look right down here, it's concave down from this y-intercept downwards. And it's nothing to do with the y-intercept, rather this happens to be the point where our tangent line crosses our midline. And the interval where our tangent function is concave down is going to be in between negative 2 pi and 0, where we exclude negative 2 from our interval because there's a discontinuity there. In the same way that we would exclude positive 2 pi in this positive interval for concavity up because it's also a discontinuity. For part A and B really of part D, we want to state the interval for concavity down is from negative 2 to 0, while the concavity up is from that 0 all the way up to 2 pi. That final part here is to identify where these points of inflections are located, and those points of inflections are located right here where that d value would occur for that midline. These points of inflections are when our tangent function changes from being concave down to concave up. It's still always increasing, or in the case we have a negative a value, always decreasing. Now, for example 8, for y equals negative 2 times tan of 1/2 times x plus pi plus 1, we want to find the following characteristics. My first step here is to graph this onto our TI-84 calculators, and then we want to try and set that argument inside of tangent equal to negative pi over 2 or positive pi over 2. And remember, this positive pi over 2 and that negative pi over 2 are always given and will always be constants because they come from our parent function tangent of x. Once we have these equations here, we're able to solve them for these two vertical asymptotes, where that first vertical asymptote occurs at negative 2 pi, and that second vertical asymptote occurs at x equals 0. Our next step is to find the period between these two vertical asymptotes, and the period for our tangent function just takes that b value of 1/2 and places it into the numerator of our tangent equation of pi divided by b. We can see that our period here is equivalent to 2 pi, and now we're able to describe the 5 characteristics, or the 5 transformations of our child function, where we first had a reflection across the y-axis. Second, we had a vertical dilation of a factor of 2. Third, we had a horizontal dilation of a factor of 2. And fourth, we had a phase shift left pi units. And finally, 5, we have this horizontal shift up 1 unit. This horizontal shift up 1 unit is going to be an important key factor for part D. We want to state the intervals where the function is concave up or concave down. we take this vertical shift here and we can label that here as the midline. This midline shows us where our function has that inflection point. From this inflection point, we can state that from negative pi all the way down to 0, our graph is concave down. While for part B, or the second part of part D, the intervals where the function is concave up is going to be from that inflection point onwards up into that positive direction. Now we don't want to go down that negative x for that interval, so we go from this vertical asymptote of negative 2 pi over to negative pi here. That last step is just to label that point of inflection for part E, where this inflection point occurs at negative pi plus or minus our length of our period, comma, our d value. These here for the characteristics of that shadowed function for example 8. Now, in example 9, we're working backwards. We want to match these graphs here of A through D to these graphs down here of 1 through 4. So let's try and tackle each of these individually. Let's first look at A here. For A, I can see that's equivalent to y equals positive 2 tangent of 2x. So I know it's going to be a positive type of function, so immediately I can get rid of option 3 and option 4, because both of those graphs are a negative type of tangent. Now I need to determine if it's 1 or 2, and I can see that for 1 there, it has that phase shift, and it does not have a phase shift. Part A does not have a phase shift. So this graph here has to be this y equals 2 times tangent of 2x. Now, for part B, D, and C, we're going to include these graphs here that we already solved, but try and provide some explanation as to why this graph wouldn't fit for those other graphs. For example, for part B here, we're given this negative tangent x minus 2. So we know that we can get rid of this option 2 and that option 1 because they're not negative tangent graphs. Now we need to determine between 3 and 4. For 3 and 4, the only difference here is that this vertical shift is positive, while this vertical shift is negative. So we can cross out option 4 because it has a positive horizontal shift. It's not a negative shift because we have that negative c value. Awesome. Now let's try and find out c. For c, we can cross out these two right away, just like part A, because they're negative tangent graphs. And the reason why we can claim equation C is for graph 1 is because for graph 2 here, there's no phase shift. That was our reasoning for why this one was A. Same kind of reasoning for D. For D here, we're still able to cross out these top two graphs here because they're not negative tangent graphs. And this time, we're able to cross out option 3 because this is a negative phase shift, and we want a positive phase shift because our C value here is equivalent to 1. For these kind of problems, I want you to try and identify some of these characteristics from these graphs and then grab these A, B, C, D values to create these equations. We'll showcase this here in our final example. Now, for example 10, we'll be working backwards from this graph here to derive some equation. Now that we're given a graph of this tangent function here, we want to find the following. Our first task for part A is to find the transformations of A and D. For me, my first task is to try and find where that midline is, that D value. And I kind of want to spot where those points of inflections might occur, where the graph itself is concave down and then changes to concave up. And I can kind of see that the points of inflections are occurring right around that vertical value of y equals 2. Now that I can see that y equals 2, I can try and plot these little intercept points here to help me find where those middle values are for my asymptotes. Now that I have my asymptotes, I can find where those points are for my amplitudes. And for my amplitudes here, they're right in between that midline of y equals 2 and that next unit above. So I can state that A is going to equal 1/2 while D is going to equal 2. Now for finding period, we can find it in a multitude of ways. We just need to take one point, such as an intercept point, and then measure how long it takes for that to repeat. Sometimes you might not know what an intercept point is, so we can use an actual x-intercept point down here, or maybe we just have these vertical asymptotes and we want to find the period between the asymptotes. All three of these periods should all be the same. And I can see that since the period here is a full length of pi, I can actually find part B, or for that B value here. And it will help us later on for this part E. For part B here, since period is equal to pi, we can still use that tangent equation of B is equal to pi divided by P, but since it's pi divided by pi, our B is just equal to 1. We now want to try and find that phase shift here, and notice that we can have two different phase shifts. We can either describe the phase shift as this negative C, where we're moving the tangent to the right some amount, or we can describe it as a positive C, where we're moving it to the left amount. Technically speaking, both of these C values would give us an equivalent equation. However, the simplest form of our tangent function is going to be whichever C value here has the smallest absolute value, the shortest distance. So in our case, we're going to use this negative C value here because it's the smallest, and we can see that we're going to move to the right a full pi over 4. We now just want to try and label these points of inflections using those pink values here. For those values, we just find them right in between our vertical asymptotes, where our points of inflections occur at that negative 3 pi over 4, comma 2, and pi over 4, comma 2, 5 pi over 4, comma 2. All those y values being 2, because that's when it intercepts our midline. The final part here is to try and write out that equation for the function. And as a reminder, the general form for our tangent function here is equal to y equals a times tangent of b times x plus c plus d. Notice how the general form for tangent is not identical to the general form for sine and cosine. When we're plugging in these values for a, b, and c, remember that sine and cosine have a separation inside their argument. For tangent problems, that's not needed. For today, this lesson looked for backwards thinking, going from graphs all the way down to these functions here, and we discovered how to solve out those equations for asymptotes. If you happen to have any questions, please leave them in the comments down below, and I look forward to seeing all of you guys in class. Take care.